Cool. So I will start my talk on the Willmore energy, which will be about min-max theory and Morse index. And my talk will be divided into 3 parts. First, introduction. Then I will talk about this min-max theory. And finally, about the Morse index of those Willmore surfaces. So first, we need to define what is a Willmore surface and what is a Willmore energy. And we'll start with a bit of history. It was introduced by Poisson in 1814, and we see it's the integral of the mean curvature to the square. The mean curvature is the mean, so the sum divided by 2 of the principal curvatures, Kp1, Kp2, which were introduced by Euler in 1744. And next year, it was introduced again by Sophie Germain, and it was to model elastic membranes. And Germain was inspired by the work of Poisson about this. The one-dimensional analog is the Euler Elastica, which is the integral of the geodesic curvature to the square. Another motivation for this work is to solve a problem given by the Academy of Science. So Chladni was a German physicist who came to Paris to show those experiments. So how do they go? You put some sand on a metal plate, and using, for example, the violin bow that you exercise on the side, some geometrical shapes will appear, as we can see on the pictures. So on the left, it's the ones of Chladni, and on the right, it's a modern experiment. And so it was the competition was to explain from a mathematical viewpoint how those could arise. And Poisson found also the Euler-Lagrange equation in the same year. So it seems a bit complicated like this. But if we take modern notations, it boils down to the equation, which is Laplace-Beltrami of h plus 2h times h squared minus k, which is 0. And it's quite interesting to see that before the time of Gauss, people were already considering those quantities, mean curvature and product of curvature. And the product of curvatures is the Gauss curvature k, which is a q in this equation. An interesting question is to know why did they only consider the integral of the mean curvature to the square? They could have used some factor, some factor containing the Gauss curvature. And the explanation is that Gauss had found that the first variation of the Gauss curvature is equal to 0. So it's what is written here. I don't know if it's readable enough, but if you don't consider the boundary terms, then the first variation is 0. And for boundary problems, in fact, you can't neglect this quantity, so you need to consider Lagrangian of the form h squared plus some constant times k. And you can look at Landau-Leaf sheets about it. Second natural question, so then my historical digression will be finished, is to compute this value for a closed surface. And it's a PhD subject that Poisson gave to his student Rodriguez. So sometimes writes his articles as Rodrigue. So for a sphere, he found the value 4 pi. So it was quite surprising that they could already do this at the time before the work of Gauss. And for tori, they found the value 8 pi. So there was a mistake, but a sign mistake. But it still shows that, there was already interesting work on this direction at the time. Then we need to jump to the next century, because this work fell into oblivion until Blaschke and Thomson reintroduced this quantity. And I don't think that they knew about the work of Poisson. So they were interested to study conformal geometry. And they noticed that this quantity was a conformal invariant. That is, if you take a Willmore surface and you make a conformal image of it, so translation, rotation, dilation, or inversion, then you get another Willmore surface. And the energy will stay the same too. And more generally, this two-form h squared minus k is also a pointwise conformal invariant. The consequence is that inversions of minimal surfaces are Willmore surfaces because they truly minimize this quantity. And here I should mention that if you invert an open surface and then it becomes closed, then the Willmore energy will not be the same. I mean, you will have a multiple of 4 pi corresponding to the right multiplicity that will come out. So, for example, if you invert the catenoid, I mean, the integral is 0, but the inversion of the catenoid is 8 pi of Willmore energy. Then this work was actually also forgotten until Willmore finally reintroduced this quantity in a paper in 1965. And he also showed this inequality, which is known as the Willmore inequality. He showed that the energy is always larger than 4 pi, with equality if and only if you have an immersion of a round sphere. And it's quite natural if you think about it, because if you could apply the standard method of the calculus of variation, you would show that there exists a closed surface which minimizes this quantity. And in particular, if it were 0, then the mean curvature would have to vanish identically, but then the surface cannot be closed because minimal surfaces in Rn are not closed by the maximum principle. And by the work of Mondino and Guyenne is the only conformal invariant in R3. So basically it's one of you can see this quantity as a way to measure the distance of an immersion to an immersion of the round sphere. And it appears in various fields, the Hawking mass, general relativity. So the Hawking mass is basically the up to a constant, the square root of the area times 1 minus 1 over 4 pi times the Willmore energy. So in Rn, it would be always negative. But if you have a curved space, in fact, if you take this Hawking mass of large spheres, it will converge to the ADM mass, which is well known in mathematical general relativity. So we can say that the Hawking mass will be the measure of the failure of this inequality in curved spaces, and the ADM mass will be the asymptotic defect. And the Frisch energy is a similar energy, which is also h squared plus some lower order terms. Now I should give a few words about the Willmore energy in different Riemannian manifolds. So rather than giving a general definition, I will just take the special case of the sphere. In this case, the formula is very simple. It's 1 plus h squared. In particular, it's higher than the area. So compact minimal surfaces in Sn will be also Willmore surfaces. So we have a lot of examples, for example, with the surfaces of Lawson. And by this conformal invariance, if you take a spherical projection in Rn of such surfaces, they stay Willmore surfaces. And it's well known that the spherical projection is a conformal map. Here's a famous example called the Willmore torus in R3, the torus with ratio of radii are square root of 2. And it's also the spherical projection of the product of two circles of radius 1 over square root of 2, which is a minimal surface in R3, very, very famous, known as the Clifford torus. And in this paper, Willmore introduced the following problem called the Willmore problem. So you fix a topology for a surface, and you look at the minimum of the energy. Of course, it depends on the codimension, a priori, but it will also be trivially decreasing if you take larger and larger codimension. So you can look at this quantity W of m when you get the limit when n goes to infinity. And in this table, we can see the different values. So for the sphere, it's 4 pi. For the projective plane, it's work of Kussner and Bryant and others. So we see it's first 12 pi and then it drops to 6 pi and then it's always the same. And for the torus, it's probably the hardest case. It's a famous work of Marquez and Neves in 2012, where they showed that the minimum of the Willmore energy for surfaces of genus at least 1 will be attained uniquely by this Clifford torus. I mean, or this Willmore torus is the same, up to conformal transformation. And they showed also that for surfaces of higher genus, so this sigma g, where G is at least 2, will be strictly larger than 2 pi squared. And the upper bound is because we can estimate, for example, the energy of Lawson surfaces, and and they are embedded. And we'll see later that it shows that. No, it doesn't show it, but yes, we'll come back to this point later. So for the higher codimension, we can in fact conjecture that Marquez-Neves result will stay true. It will be always less than equal to 2 pi square. And we have some reasons to believe this. For example, there's a work of Kushner and Wang, where they showed that the Willmore index of the Clifford torus in S4 is 6, and it was 5 in the torus, which is one of the basic ingredients. So, and for higher genus, it's a work of Kapuleas and Wiggle, where they prove that the Morse index of those Lawson surfaces sigma G1 is 2G plus 3, and so there's some linear growth, and it's kind of expected that there will be the minimizer in higher genus, but so far there's